Okay, so now we are going to look at two-phase locking protocol. Okay, so previously we had been discussing uh, the use of a precedence graph, generating a precedence graph in order to decide whether a schedule is serializable or not. And we also stated that in practical situations, it is not possible to actually come up with a complete schedule of multiple transactions and then generate a precedence graph. So the alternative is to have some sort of rules to decide, that is to ensure that serializability happens as and when the schedule or the set of transactions get executed. So what are the different methods? So two-phase locking is the most popular sort of algorithm for it. Now, what is two-phase locking? So before that, we have to come across or understand what a lock is. Okay, so even in the subject operating systems, you might have come across um, critical sections and how synchronized different processes can be synchronized using various methods like semaphores and so. Lock also you must have come across there. Basically, a lock is a variable which is associated with a data item. And so lock itself is a variable which is associated with a data item and it describes the status of the item with respect to the operations which are applied on it. What is its status? Can I access this particular variable at this time or not? That is what a lock does. Okay. So for every data item in the database which needs to be accessed, there is a log associated. So as we said, logs are used as a means for synchronizing access by concurrent transactions. So in the case in operating systems, you must have in multi-processing systems or multi-programming environments, multiple processors might access the same data item, right? So that is why synchronization was required there. So it is the same concept which is being used here also. So you have got different types of logs. First of all, we will look at what is a binary log. Okay, so as the name itself suggests, a binary log has two states or two values associated with it. Either the variable is locked or it is unlocked. So you can say locked means 1 and unlocked means 0. Now, if the value of the lock is 1, then the item cannot be accessed by database operation. It's already locked by some other process or some other transaction. So it cannot be accessed at this time. Okay. And if the value is 0, then the item can be accessed when requested. And when it is accessed, the lock value is being changed to 1. So this is the concept. The state of the lock is represented using this notation. This is a state, and this can take a value of either 0 or 1. Um, and there are two operations also associated with the lock. This is a state of the system, and in order to lock it or set the value to 1, you have got an operation called lock item, and there is unlock item also. And so a transaction requests access to an item X first by issuing a lock operation. So in order to access a database item, either a tuple or a variable, first of all, it has been locked so that it is not being accessed by, say, another transaction. Right. Say, for example, we have a running example has been, say, IRCTC, booking seats on IRCTC website, let us say. So, uh, the data item which is being logged is a seat, the number of seats available on a train or a particular seat. So, when you are trying to read it or read the number of seats which are available, then you have to lock it. Otherwise, another transaction also will try to access the same data item and it can create problems. Okay, so lock and unlock are the operations associated with this particular variable. So how can lock and unlock items be implemented? So if the state is 0, that is if the variable, the lock is in the unlocked state, the state is 0 means it is in the unlocked state, then since you are requesting for a lock, the value will be set to 1. Otherwise, we know it is being used by some other transaction. So you have to wait until lock is set to 0 by that transaction. So when that happens, that transaction or some process will actually wake up our transaction because we will go into wait state. And similarly, unlock item is it is simply by setting the value to 0. And if any transaction is waiting on this particular lock, it has to be woken up also. And we have to remember that there should not be any sort of context switch happening between these operations. All this has to happen as a single unit, right? Because what happens otherwise you're checking whether lock is equal to 0, and if you context switch to something else, then that particular transaction will also find that our lock is 0. So both of them will try to access it if you come back. So all these concepts you already are familiar with when you have studied operating systems. Okay, so a lock and unlock has to happen as a single atomic operation or indivisible operation. Okay, so this is the concept of a binary lock. So whenever you want to access a data item, first of all, what you say is lock lock item on that particular. You have to say if you want to read variable x. First, you have to say lock the variable x, and then you do a read x, and then you have to do an unlock item x. This way multiple transactions will not try to access the same data item. Now, this sort of binary locking system, the disadvantage of binary locking is that it is too restrictive for data items. When, let us say, two transactions are trying to read the same data item, say X. When you're trying to read it, there is no point in locking it up, right? So when you're reading, for reading purposes, we can allow multiple transactions to actually access it. So we have a different sort of locking mechanism for that, right? So that is called shared and shared exclusive, or shared locking for read operations and exclusive locking for write operations, or you can also call it read write locks. That is another sort of locking mechanism. Okay, so in this mechanism you have got three operations. There is a read lock, there is a write lock, and an unlock. Instead of simply, we had only two operations here. In the case of binary lock, it is a lock item and an unlock item. But here what we are saying is, here it is a shared lock in the case of read. So read lock and write lock are different in this case. So we have got three operations associated with this sort of locking mechanism: read lock, write lock, and unlock. And again, a lock associated with item X, lock X, now has possible states: read locked, write locked, and unlocked. Okay, so a read locked item is also called shared lock because other transactions are allowed to read the item, and write locked or exclusive lock because a single transaction exclusively hold the lock on the data item. So this is these things we have already come across. So how do you implement these things? Okay, what is read lock operation? How does it work? In read lock, the characteristic we said is multiple transactions can try to read it, but if you are reading a data item, if someone else is trying to write it, then that is not possible. Okay, that is a characteristic. So what happens is, again, you state of the lock is if it is unlocked, that is no one has actually access to this particular variable, then you can set the state to read lock, and the number of reads is set to 1 because multiple transactions can read the same data item. So you're maintaining a variable called number of reads, and it is initially set to 1 if it is in the unlock state. Otherwise, if it is already in read lock state, means it has already other transactions are accessing it. So you simply have to increment the number of transactions which is reading that. Okay. Now, if it is already in, say, write lock state, or else it is in a write lock state, then you have to wait for an unlocked the state to go to unlock in order to actually access it. So unlock the lock manager will wake up this particular transaction, and then you can go back here. Okay, so this is read lock. Now write lock means it only can take control of that particular variable when the state of the system is unlocked. Okay, in that case, you can set it to write locked. Otherwise, you will have to wait because a read lock transaction cannot be accessed by another transaction for write. So this is how it is implemented. Again, like we said earlier, this is a read lock operation. It means it has to be done as a single unit. Similarly, this write operation has to be done atomically or as a single unit. Now, in the case of unlock, unlock means it's already locked. It can be either read lock or write lock. If it is write locked, then you simply state to change the state to unlock and wake up one of the waiting transactions, which will be there in a queue. Now, otherwise, if it is in a read lock state, now you increment the number of reads by 1. If the number of reads reaches 0, means there are no transactions which are doing a read, then you can set the state to unlock and wake up one of the transactions which is waiting, probably waiting for a write operation. Okay. Okay, and these are different locking mechanisms which we discussed, but here the responsibility of calling the read lock and write lock operations rest with the programmer itself. Okay, so transaction T must issue the read lock or write lock before any read item operation is performed in T. Similarly, a transaction must issue the operation write lock before any write item X operation is performed, and the transaction T must issue operation unlock after the read item or write item operations are completed. And these are some of the rules which the programmer, because the programmer is the one which is responsible for doing all this. So the programmer has to follow these rules for this locking mechanism to work. And similarly, a transaction T will not issue a read lock operation if it already holds a read lock or write lock. Okay. Now, similarly, a transaction will not issue a write lock if it already holds a read or write lock, and it will not issue an unlock operation unless it already holds a read or write lock. So these rules have to be followed in order to use the locking mechanisms. Another concept is the concept of upgrading and downgrading of locks or lock conversion. That is whether you can upgrade from a read lock to a write lock and downgrade from a write lock to a read lock. That is another mechanism which is possible. Okay. So if T is the only transaction holding a read lock on X, at the time it issues a write lock, then the lock can be upgraded. Other transactions are not reading this variable X. Only this particular transaction T is reading it. Then after some time, if a write lock X is issued by the same transaction, it is possible to upgrade the read lock to a write lock. And it is also possible for a transaction to issue a write lock and then later downgrade the lock by issuing a read lock operation. So this is another what method which can be followed. Okay. Now this is an example of using read lock and write lock mechanisms. But what is being stated is using binary locks or read write locks in transactions does not really guarantee serializability of schedules on its own. Okay, so it is to illustrate that this particular example is shown. So if you look at this here, what happens is in transaction T1, a variable called B is read and the value is reduced by 50. And okay, so the logs we are not discussing and it is being written back to database. And similarly, after that, read the variable A, add 50 here and write it back. So we can think of, let us say, this can be thought of as B is one, say, bank account where you're deducting 50 rupees and it is being transferred to. We can think of it that way. And here, what is done is in order to ensure that multiple transactions do not access the variables which are accessed here, there is a lock operation. So lock x b, because b is going to be read and written, so you have a lock. This is a binary lock, so you're locking the variable b, and after it has been read and written, there is an unlock operation. Similarly, lock on A is also there. After it is read, change is made, write back, you've got an unlock operation. Okay, so this is another transaction. What happens here is you are reading the variable A, and you are also reading variable B, and you're displaying A plus B. Okay, so this is basically what happens in these two transactions. Now, let us say if we have transactions, the serial transactions T1 and T2, or T2 followed by T1. Either way, if A is equal to 100 and B is equal to 200, so if it is either uh, of these serial transactions, the sum which is displayed after this transaction will be 300. Okay, so you can go through it and verify actually. That is the actual correct. This is the output of a serial schedule. Okay. Now let us say this is an interleaved way of executing transactions T1 and T2. T1 and T2 are interleaved. So one set of operation is done, that is you have read the variable B, made the modification by reducing 50, and then this transaction is executed, and then you go back here, then update this. You can actually see it here, the value which will not be correct. It will actually be 250 if you actually go and look at it. Now the problem is, look what we said is you're deducting 50 from one account and it has to be updated in the other account. In between, we are trying to do a you're calculating a sum. Basically, at this point, the database is in an inconsistent state, right? Because you have only deduced the 50 rupees, you have not updated it here. Okay, so so even if you have locking mechanisms, it is really not necessary that uh, the what the schedules can be serializable. It is not necessary that the schedules are serializable. So for that, something extra which is needed. So to guarantee serializability, we must follow some additional protocols concerning the positioning of the lock and unlock operations. So that for that, the protocol which is best known is called two-phase locking, which we will be looking at next. Okay, so two-phase locking protocol, what it says is, so if for a transaction to follow the two-phase locking protocol, uh, in order to say that a transaction or a schedule is follows this two-phase locking protocol, if all locking operations, whether it is a read lock, write lock, has to precede the first unlock operation. So first of all, at the beginning, you have to ഏറ്റവും beginning that is before any unlock happens, all the read lock or write lock operations must have happened. That is what two-phase locking protocol is. And so if you look at any schedule, okay, or even any transaction, it is divided into two phases. The phase in which all the locking happens, which is called the expanding or the growing phase. Okay, that is when all the locking happens, but no unlocking happens. And similarly, shrinking phase, which is the second phase during which all the unlock happens. And in that time, no locking happens. And if any lock conversion is allowed, then upgrading of locks must be done during the expanding phase, and downgrading of locks must happen only during the shrinking phase. That is the rule for two-phase locking. Okay, if you look at these two transactions which are given, here you have got a read lock, and then the item is read, and then you have an unlock. So, and after that, there is a write lock. So, this does not follow the two-phase locking protocol. So, in order to make this follow the two-phase locking protocol rule, what is to be done is we have to move this unlock down here. That is, all locking should happen first before the unlock phase happens. So that is what is done here. You have got a read lock, a read item, then you have the write lock. Instead of the unlock, you do a write lock here, and then you have an unlock. So this is the growing phase. This is the growing phase when the all the lock locks are taken, and after this point you have the releasing of locks. Okay, unlock happens only after this. So that is what two-phase locking means. And so it can be proved that if every transaction follows two-phase locking protocol, then that schedule is guaranteed to be serializable. Basically, that is what we want. We want the schedules to be serializable, right, to ensure correctness. So there is now no need to test for serializability like we did earlier with the precedence graph and so on. Okay, so if we are enforcing the two-phase locking rules, we can enforce serializability. But the only problem is because of delaying of unlocking, there is less concurrency. So more the concurrency, more the CPU utilization. So that sort of concurrency is reduced, but we are able to ensure the correctness of the schedule. Okay, there are different variants of two-phase locking protocol. The basic two-phase locking protocol, which we earlier talked about, is all locks are acquired before all locks are released. So there is a acquiring phase or growing phase, and there is a releasing phase for locks. And another variant is called the conservative or static two-phase locking. That is very restrictive in the sense that first you have to pre-declare the read set and write set. Pre-declare means in case of all transactions, we have to identify the read set and the write set. I hope you remember read set is a set of items which are being read and write set is a set of items which are written in the case of a transaction. So we have to identify, pre-identify what is a read set and the write set, and at the very outset, before the transaction starts executing itself, or before any of the operations happen, we have to lock all the items. So that is what this conservative or static two-phase locking is. And this is deadlock free, but it is not feasible because uh, locking all the items, first of all identifying the read set and write set as well as locking all the items at the beginning might not be feasible. Okay, okay, more popular two-phase locking is a strict two-phase locking. Okay, and this strict two-phase locking actually guarantees strict schedules. So remember we had talked about strict schedules. So strict schedule is a schedule in which if you have say got transactions T1 and T2, and T2 commits only after T1 commits if T2 has read some data which T1 has written. Okay, if T2 has read some data item that T1 has written, then only after T1 commits will T2 commit. That is the definition for a strict schedule. So strict two-phase locking protocol ensures strict schedule, which is what we need. Okay, so in the case of strict two-phase locking, a transaction T does not release any write locks. Only write locks we are talking here. Okay, it does not release any write lock until after it commits or aborts. Hence, no other transaction can read or write an item that is written by T unless T has committed. So that is a definition for strict schedules. Okay, strict schedule, unless transaction T1 which has written something commits, the other should not commit. Okay, that is ensured using locks, write locks. Okay, and we have a more restrictive version of strict two-phase locking, which is called rigorous two-phase locking. And in this case, a transaction does not release any of its lock. Here we are talking about only write locks. Transaction T does not release any write locks until after it commits or reports. But this is a more restrictive version. A transaction T does not release any of its lock, either read or write, until it commits or reports. Okay, so this is the way in which serializability is being ensured by two-phase locking protocol, and all these are taken care of by the concurrency control subsystem of the database management system. So it is responsible for generating both the read and write logs. So the actually the in the program or in the transaction, the transaction only issues read item and write item and so on. It is the responsibility of concurrency control mechanism to appropriately issue the read lock and write lock at the appropriate points, ensuring two-phase lock. When two-phase locking is ensured, serializability and correctness are also ensured. Okay.